Get to know your gas laws part 2, and this is going to introduce you to a few key scientists that are involved in terms of looking at the behaviour of gases and how gas volume, pressure, temperature and the number of particles are intricately linked together. This involves a bit of calculation, so I'm going to be explaining a few of the maths involved and a few of the observations that these three gentlemen here have done to explain how these gases behave. So, as I said before, we're going to look at how the volume of a gas is affected by temperature, and the volume of a gas is affected by pressure, and the volume of a gas is affected by the number of particles. We're going to look at these individually, and then we're going to combine the equations that we have looked at into one general equation that you're going to use every single time, just so you don't have to remember 3 different equations, you just only have to remember 2, which makes it a bit easier for you. For a start, we're going to look at Charles's law, and this is Jacques Charles, and he looked at how the volume changes when we change the temperature. This is all pretty trivial stuff for you, but we're going to have a look at a demonstration to explain how this all works. What Jacques saw was if you change the temperature of a gas, you're going to change its volume. Now let's have a quick look here at a demonstration. This involves a 44-gallon drum being heated up. We've done this at school last year, where we're heating up the 44-gallon drum for a while. We'll put it onto a burner, and then we're going to close off the 44-gallon drum. So what's happened is the gases inside this 44-gallon drum are at a higher temperature, at a very high temperature. What we're going to do is close off our drum and place it into an ice bath. When it's in the ice bath, what's going to happen is the gases inside the 44-gallon drum are going to cool right down. And what happens? The volume decreases dramatically. All right, you can see it here at another angle, and bam, volume decreases dramatically. This is because volume is proportional to temperature. The higher the temperature, the greater the volume. The lower the temperature, the smaller the volume. This is true when we're trying to keep the pressure the same and the number of particles the same. So if you keep the pressure the same, number of particles the same, volume is directly proportional to temperature. If we plot this on a graph, we can see this graph here, where we have volume on the y-axis and temperature on the x-axis. So as you increase the temperature, you're increasing the volume. And this is remember, with pressure constant and the number of particles constant. Because we put that cap on, nothing comes in, nothing goes out, number of particles are constant. And atmospheric pressure is not changed. If we want to write an equation for this graph, this is obviously you can see it's a linear graph. So what we're going to do, we're going to write down that volume is equal to a constant called K, okay, times the temperature. Okay, because we have a straight line, its volume equals something times temperature. Now, I'm going to do a bit of a rearrangement of these and I'm going to put the temperature underneath here. So volume over temperature is equal to a constant, that means. Okay, this constant for the set pressure and for a set number of molecules will not change. So we have a ratio here for a certain pressure and for a certain temperature of volume to temperature. What this means is that if we change the volume, we're going to change the temperature. So we can link these two things together, and what Jacques Charles came up with was this relationship here, where V1 over T1 is equal to V2 over T2. Okay, this is known as Charles's law, where the volume and temperature are intricately linked at a set pressure and with a set number of molecules in there. We have an initial volume, an initial temperature, and a final volume and a final temperature. This is very similar to our concentration and dilution equation, but obviously we have V1 over T1 equals V2 over T2, and that's our Charles's law. And that's known as Charles's law because he's the guy that saw this link between volume and temperature at a set pressure. Okay, got another video here which just demonstrates it again. This is for showing how if we cool down a balloon in liquid nitrogen, what happens? The volume decreases greatly. Obviously, you can see that the balloon is deflating. And then if you take it out of the liquid nitrogen, it heats back up to room temperature, and the volume comes back to room temperature, where we got a direct correlation between the volume inside the balloon and the temperature of the gases inside the balloon as well. It's nice to note that the temperature should always be measured in Kelvin. When you're doing these equations, temperature should be changed into Kelvin, and the Kelvin scale is a scale that goes down to absolute zero, and it's known as the degrees scale, adding on 273 degrees Kelvin. So if we're looking at some different temperatures, 25 degrees Celsius is equal to 298 degrees Kelvin. Negative 56 degrees Celsius is equal to 217 degrees Kelvin. And 100 degrees Celsius is equal to 373 degrees Kelvin. So each time you're dealing with temperature in terms of a gas law like this, you have to change your temperatures into Kelvin. Otherwise, it might not work. Let's move on. Robert Boyle. Robert Boyle looked at the link between volume and pressure. And we've got a nice demonstration from the guys at Kent Chemistry. I've just taken their video, and I'm going to explain this video where we have a marshmallow man going to be put and exposed to a low pressure. Okay, so let's put our marshmallow man in our bell jar. There he goes. What we're going to do is take the volume, or apply this to a vacuum. So to suck all the air out of this vacuum here, which is going to really decrease the pressure in this bell jar. And what we can see is our marshmallow man, our Stay Puft from the Ghostbusters, what he's doing is hugely increasing in volume. Okay, as we decrease the pressure, the volume of our marshmallow is increasing right up into the point where he popped and he starts to deflate again. But you can see here quickly, go again, let's watch him turn on the vacuum pump, and there is Marshmallow Man increasing in volume. He's getting bigger. What this means is that the volume is inversely linked to pressure. So that means if you decrease the pressure, you're going to increase the volume. That also means if you increase the volume, you're going to decrease the pressure. Or if you decrease the volume, what you're doing is increasing the pressure. All this must happen at the same temperature and with the same number of molecules. All right, the same number of molecules are in our Marshmallow Man. Okay, so therefore the volume of the Marshmallow Man is increasing, and the Marshmallow Man is not changing temperature, so therefore his volume is increasing. We can plot this on a graph again and have V equal over volume on one side and pressure on the other side. As we increase the pressure, volume goes down. As we increase the volume, pressure goes down. And you can see that relationship there. A mathematical relationship for that is V equals some type of constant over pressure, okay? Where V is the volume, P is the pressure, and this is just a constant which links those two together. I'll do the same type of thing and rearrange it. So I get volume times pressure is equal to a constant. What that comes up as is that V1, P1 equals V2, P2. And this is Mr. Boyles Law, because he's the person who first of all linked volume and pressure and wrote about it. Okay, that should have come up before that, but you get the idea. Same type of thing as pressure, so same type of thing as temperature, but we're using pressure. And because it's inversely linked, these two things are side by side. So therefore you have the link between volume and pressure, known as Boyle's Law, V1, P1 equals V2, P2. An initial volume, initial pressure, changing one of those two is going to affect the other one in this relationship. And remember that this is where number of particles and temperature must be constant. Let's move on and look at Avogadro. Here's our man, Amedeo Avogadro. We learnt about Avogadro because he'd worked a lot with moles, and he's not doing anything different this time. What he looks at is the volume that is proportional to the number of particles. And this is a very, very, very simple thing to understand. If you blow into a balloon, the more you blow into the balloon, the greater the volume is, the larger the balloon goes. So you can easily see that if we have volume here on one axis and number of moles, we get an increasing, a large increase in volume for a large increase of number of moles. And it is a linear relationship at a constant pressure and at a constant temperature. So you get the idea there. Increase in moles increases volume. Once again, we'll plot this and we'll write a equation for it, where V equals Kn, and K is a constant. Okay, so there's a constant gradient here because it's a linear relationship. Rearrange this in the same way that I rearrange my temperature equation to get the constant by itself. Means I have V over N equals K. What this means is that I have a ratio of V to N, and that will not change, that ratio will not change if we keep the pressure and temperature constant. So we can have V1 over N1 equals V2 over N2. Okay, and that is known as Avogadro's law. Okay, it's his law because he dealt with particles and volume. Now, there's interesting things that you should probably know that we can use to convert straight from number of moles to volume, and these are what the basically the K value here for certain temperatures and pressures that we use a lot. Our temperatures and pressures that we use a lot are standard laboratory conditions, which is 25 degrees Celsius, and 1 atmosphere, which is 101.31 kPa, and standard temperature and pressure, which is 0 degrees Celsius at 1 atmosphere. Now, for standard laboratory conditions, we have a molar volume of 24.5 litres per mole. So no matter what the gas is, whether it be nitrogen, whether it be argon, whether it be helium, 1 mole at 25 degrees Celsius and 1 atmospheric pressure, you'll have 24.5 litres of volume for that thing. So it doesn't matter what type of gas it is, 1 mole of that gas will always occupy a set volume. Okay, for standard temperature and pressure, 1 mole of gas will always occupy 22.4 litres. Okay, obviously you can see the link between here, different temperatures, different volumes. Okay, but you need to know, well, you don't need to know these, you can get by without it, but it's nice to know as a shortcut from our next couple of equations that this is a standard figure. So if you have 1 mole of any substance, it will occupy this much volume. So it's interesting, it's nice to keep that in mind at standard laboratory conditions. If you move away from standard laboratory conditions, you need to use one of the next equations that I'm going to present you with anyway. But they're the 3 gas laws, they're the 3 main gas laws that are named after people. However, rather than learning all those 3 different gas laws, what I'd like you to learn is the following, which is the general gas law, the combined gas equation. And this links in all the things that we've talked about. This links in the fact that volume is proportional to temperature and particles and inversely linked to pressure. So therefore V equals Knt over P, where this K is a constant which is linking all these things together. It takes into account all the other Ks, the constants from the last 3 slides. So if this is how it works, what we can come up with is in the same way that I did the last one, is that Vp over Nt equals Vp over Nt, where we have an initial conditions and our final conditions. Okay, this is combining the last 3 gas laws that we learned. So Vp over Nt equals Vp over Nt. Your initial conditions, multiply the 2 volumes and the temperature thing together, are equal to the final conditions. Why do you need to know this and not the other ones? Why is it important to remember this one rather than each other 3 ones? Well, first of all, it's easy to remember just one equation. And what you can do is get those other equations from this equation. How do we do that? When a question deals with changing temperature, pressure, or volume or mole, you should start with this equation. All right, that's what it has said. You need to remember this one, okay, more so than the other ones. What you need to do is cross off the things that are held constant. For example, a question will ask you if you have a change in volume, okay, it will expect you to have, well, if you have a change in volume, what will the new pressure be? It will probably say that the number of moles is held constant and the temperature is held constant. What we can do is cross off these things that are held constant and we'll end up with Vp equals Vp, which is Boyles Law. Okay? If you remember this way of doing things, so crossing off the things that are held constant, then write down your initial and final and the unknown, then solve for the unknown, that's how you will work out how do you do these gas laws, use these gas laws. You need to know that Boyle dealt with pressure, you'll need to know that Avogadro dealt with number of moles, and you need to know that Charles dealt with temperature. How you remember that is up to you. But if you remember this gas law, this final combined gas equation, you'll be on the right track anyway. What you've got is I'll have a few examples of these problems on a new video. So you should be watching. You should go and watch those examples of questions, and then from the textbook you've got these questions which deal with this combined gas equation. Okay, remember this equation and cross off the things that are held constant, and it'll help you calculate different types of gases and different changes in gases. This is the last chapter in the book. I think it's chapter 21, give or take. So these refer to the Heinemann textbook, so the Heinemann Year 11 textbook, the green one. Let's move on. So you should really pause this and go off and look at these examples, do these questions, and then come back for the next part of this podcast anyway. Which is the general gas equation. The general gas equation uses this. Okay, the general idea that the volume is proportional to all these things. Okay, but it doesn't actually take this form. The form that it takes is PV equals nRT. So what we have is the pressure comes across here, so we just have a one-liner things. N is the number of molecules, the number of mole of molecules, and T is the temperature in Kelvin. This R is a constant value, so the K here is given the value capital R, which is known as the gas constant. Here are how everything is measured. Pressure must be measured in kPa, so you need to be able to change all your pressures to kPa. Volume is always measured in litres. Well, it always was measured in litres. We haven't changed that at all. It's always measured in litres. Mole is measured in mole. Interesting. Sorry about that. And our R value is 8.31. I haven't given you the proper units for this. It's not mole, it's actually mole degree Celsius per kPa per Kelvin. Okay, that's what this R value is. But all you need to know is that it is 8.31. The temperature is measured in Kelvin, and we talked about how to convert to Kelvin beforehand. This is what you need to remember, that P is always in kPa, V is always in litres, mole is always in moles, R is always 8.31, and temperature is always in Kelvin. So if you convert everything, or your unit, or your amounts to these measurements, you'll use 8.31. You must use, and what this allows you to do, is convert moles to volume at any pressure, at any temperature, because this is our general gas equation. This is usually what you use when you go and do stoichiometry, and that's what the next slide talks about. So our general gas equation is PV equals nRT, and this is what you need to know, and you need to know how to use this. There are tons of questions in the textbook about it, and we're going to go and look at those in a little bit. We've got sample example questions here, see example questions, videos, and here are a whole bunch of questions which deal with this gas equation. All right, so This is again from the Heinemann textbook, so you need to go and do these equations with this gas equation. Using this gas equation is basically looking at stoic. Okay, basically this gas equation means you can convert number of moles into volume or into pressure or into something else. So what you'll generally do is find out if you have a mass of magnesium reacting with hydrochloric acid, what you can find out is the volume of hydrogen gas that is going to be created. And that's just using your simple stoic. And what you'll need to do is review all the questions, all the chapters, and then what you're going to do is get ready for your practical exams because we are done with Unit 2. Hopefully this has helped you. Hopefully this has explained a little bit about the pressures and the gas laws for you. What you're going to need to do really is look at my sample videos for examples of how to use these gas laws and then do a whole bunch of problems yourself. Okay, get stuck into some stoic and do a few of the stoichiometry problems as well in terms of mass to volume stoichiometry or concentration and volume to volume stoichiometry, if you know what I mean. Anyway, we're done. We're finished. Watch the sample videos, and if you have problems, give us a yell, email, or see me at school.